Next, we will study the Poisson summation formula. This is the theorem, very useful. Suppose f is a non-negative function such that the integrable because it is non-negative, this is equivalent that it is absolutely integrable. Okay, and then we assume that it is increasing 1 minus infinity 0 and decreasing 1 0 to positive infinity. That is, the graph of this function look like this. Okay, the function looks like this. Then we have mean value of the left and right limit of f at integer point, summing over all integer point equal the sum of this integral f t expression of 2 pi int dt. In the language of Fourier transform, this is the right hand side is just the Fourier transform of f at what point? I lambda t, lambda it 2 pi n. Okay, so this is the so-called Poisson summation formula. From this we can say that if f is continuous at the integers point, we don't require it to be continuous everywhere. If f is continuous at every m integer, then fm plus equal fm minus, and the result becomes fm equal the sum of the Fourier transform at the value 2 pi n. Okay, that is, if we want to compute the sum of f at integer point, you can go to compute the value, the sum of the value of f of the Fourier transform of f. Okay, so this is the Poisson summation formula. Now we prove this result. To prove this result, we let capital Fx to be the sum of this series of functions. For every m, that is gmx equal fx plus m. So this is simply the sum of gmx. Okay, this is the series of functions. So f is decreasing on 0 infinity. So m minus 1, m plus 1. For negative m plus 1, m minus 1. Okay, the function f is like this, decreasing for positive value and increasing for negative value. So we have for every x, for any x in the interval 0, 1, our absolute value of f m plus x. This is just fm plus x because our f is non-negative. So fm plus x, x because x is between 0 and 1. So for positive m, m plus x is this part. For positive m, and for negative m plus x is this part. So the value of fm plus x located here or here. It does not exceed m. Maybe I use another color. It does not exceed the m here or m plus 1 here. But this will not greater than the integral of f over the interval minus 1 to m plus 1. So we have this inequality. This will not greater than m minus 1, m plus 1 of f. This denoted by am. Okay. Then, but the sum of am, m from negative infinity to positive infinity, is the sum of m minus 1, m plus 1 f. This will not greater than twice of the integral epsilon f. And this is finite because f is integrable. F is non-negative and integrable. Okay. So the general term in this series of functions is controlled by the general term of a numerical series. We are studying a series of functions, but now this is a convergent series of sigma am is a convergent series of numbers. The general term of the series of functions, that is the fm plus x, is controlled by the am, the general term of the convergent series. So by the Weier's class, we know that the series converge uniformly on the interval 0, 1. For every x in 0, 1, it converges, and it converges uniformly in the interval. Okay. So this is the first conclusion we need to get. The second is that f is periodic. F is one periodic. That is easy. Fx plus 1 is the sum of fm plus x plus 1. Replacing the x by x plus 1, we obtain fx plus 1. But this is just the sum of fm plus x, that is fx. So f is one periodic. Thirdly, f belongs to f is a boundary variation on the interval 0, 1, because fx is the sum from 0 to infinity fm plus x plus the sum from 0 to minus infinity fm plus x. But for the second sum, we can write it in another way. That is 0 infinity fm plus x minus 1 infinity. Sorry, this is minus 1. not 0. So this is minus 1. This is minus 1. So so we replace this m by minus n. So for the n is n from 1 to infinity, f x minus n, and a negative sign, which is a negative sign, because this is negative. Okay, so we see that this is increasing because f is increasing for positive value, and this is also increasing. Increasing, decreasing. Maybe I make something wrong. No. This is decreasing because n plus x is positive, and f is decreasing, and also this is also decreasing because f x minus n is increasing. Because x minus n is negative, therefore fx minus n as a function of x is increasing, which the minus sign here, it is fx minus n is increasing, which the minus sign it is decreasing. So our capital F is the difference of two decreasing functions. Then you switch these two decreasing functions with a minus sign, you will obtain that this capital F is the difference of two increasing functions. Okay, so this proves that F is bounded variation. So F is bounded variation. Now we have a Jordan test. By Jordan test. By Jordan test, we know that the Fourier series of f converge to the mean value of fx at the mean value of the limit, right and left limit of f at x. By Jordan test, we have that is fx plus fx minus divided by 2, the mean value, equal the Fourier series of capital F at x. The Fourier series of capital F at the point x converge to the mean value of this left and right limit of capital F at x. But for convenience, the Fourier series we use the complex form or exponential form. We instead of using sine and cosine to save space, we use the exponential form. Alpha n exponential of 2 pi nx. Here alpha n is given by 0, 1 capital F x exponential of minus 2 pi I n x dx. This is the complex form of Fourier series. For this alpha n, we can use the definition of capital F m from minus infinity f m plus x, then exponential minus 2 pi I n x dx. Okay, then we can switch the order of integration and summation because the series is converge uniformly. Okay, we have just proved that the series for capital F is converged uniformly on the interval 1, 0, 1. So we can switch the order. We can switch the order of the summation and the integration. That is, we can integrating term by term. So this gives us sum m from minus infinity, positive infinity, then integral 0 to 1 f m plus x exponential of minus 2 pi ln x dx. And we make a change of variable. This can be written by m from minus infinity. M plus x, we denote this by t. Then t is for m to m plus 1. Ft exponential minus 2 pi ln. Our change of variable is m plus x dt. Then x is t minus m. So here we have t minus m dt. But exponential of 2 pi ln t minus m is exponential of minus 2 pi ln t multiplying exponential of 2 pi ln m. Nm is an integer. Exponential of an integer. Exponential of an integer multiple of 2 pi I is 1. So this term can be written by ft exponential of minus 2 pi ln t dt. The m can disappear because the exponential of 2 pi ln n is 1. Okay? So finally, this can be written by minus infinity, positive infinity, ft exponential minus 2 pi ln t dt. This is the alpha n. This gives us the alpha n. So we obtained that capital F x plus capital F. Maybe I will write it in another form. The sum of, I write the right hand side first. The sum here we write this n from minus infinity alpha n. We use the expression of alpha n we obtained. Alpha n is ft exponential minus 2 pi ln t dt. Then exponential of 2 pi ln x equal half of capital Fx plus fx minus. By the definition of capital F, this is the sum n from minus infinity half of f m plus f m minus. Because capital F is the sum of, remember, capital F x is the sum of f m plus x. Therefore, the left limit is the sum of the left limit of f at m, and the right limit is also similar. So this is just oh no, I forgot to write x. Sorry. Here I have a mistake. I need to write this in. I should write this equal. Maybe I will use another color. Equal the sum n from negative infinity, positive infinity, f m plus x plus f m minus x, m plus x minus divided by 2. This means the left limit and the right limit at x of this function. And then set x equal to 0. Set x equal to 0. this term is 1, and this term become fn plus, and this term become fn minus. So this gives us the result of the theorem. This is what we want to prove. That is this equality. Okay. So this proves the the Poisson summation formula. And in the proof of the Poisson summation formula, we need the Jordan test. Jordan test play a crucial role because we want the Fourier series of capital F to converge at x to the mean value of the left and right limit of capital F at x. We need this result, but we have not discussed the Jordan conversion test. Okay, so we discuss this here. This is the Jordan test. So f is integrable. F is integrable, absolutely integrable. We use this notation. LR denote absolutely integrable function. And 2 pi periodic. And also, if f is bounded variation in a neighborhood of x, then the Fourier series of f at the point x, the Fourier series of f converge to the mean value of the left and right limit of f at x. Okay, this is the so-called Jordan test. So how to prove this? In our previous lecture note, you can check the formula 614 in previous lecture note. We have 4s equal half of fx plus fx minus. For such s, our Sn minus s, we have a formula for Sn minus s, right? Remember? Snx is the partial sum of the Fourier series of f at the point x. Subtract s, that is 1 over pi 0 delta. The phi u, at the moment we write phi u. The phi u there is f, maybe we write phi t. Phi t there is fx plus t plus fx minus t minus 2s. This is our phi t. Using maybe you remember in our previous lectures when we discussed the convergence of a Fourier series, we have a formula for Snx minus s, the partial sum of the Fourier series at the point x and s. Okay, that is phi u. We write phi t over t sine n plus a half t. Then the difference, this is not equal. This is not equal, in fact, but the difference is a very, very small quantity which will converge to 0. Okay, so with the s, which this s, we have Snx minus the mean value. That will give us 1 over pi. 1 over pi. Then 0 delta fx plus t plus fx minus t minus fx plus fx minus divided by 2t. sine n plus a half t dt. This can be, and also the small term. This can be written by 1 over pi 0 delta fx plus t minus fx plus divided by t. Then sine 2n plus 1 2t plus pi 0 delta fx minus t minus fx minus divided by t sine 2n plus 1 2 t dt. Now we apply the Jordan lemma. We established at the very beginning. By the Jordan lemma, we know that by Jordan lemma, both terms goes to 0. This is the conclusion of Jordan lemma. For alpha equal 2n plus 1 over 2. Jordan lemma says that if G is bounded variation, then GT multiplying sine alpha t over t. Here is our alpha. So that is this two integral is of the form sine alpha t divided by t multiplying this function. This function, because f is BV, bounded variation in the delta neighborhood of x. So this function is bounded variation. That is gt equal fx plus t minus fx plus is bounded variation on 0 delta. Because f is bounded variation on the delta neighborhood of x. Okay, so this proves the Jordan test, which is used in our proof of the Poisson summation formula. Okay.